Welcome back. Today we'll be starting a new unit on energy. This unit really is a continuation of the last unit. In the last unit, we were learning about work and simple machines. And at the beginning of that unit, we learned that work was a transfer of energy. So in order for work to happen, energy had to be transferred from the object doing the work to the object upon which the work was done. Okay, so our definition of energy in this unit, energy is the ability to cause change or to do work, which, as I said, is a continuation of the last unit. Also in the last unit, I told you that the unit for work was joules, and also the unit for energy is joules. And remember, we talked about when the girl was lifting the tub, okay, that she added potential energy to it, and the amount of potential energy that she added to the tub was equal to the work to lift the tub. So this relationship to work and energy is important. Okay, because work is the ability to cause change, anytime there's a change in anything, it's a result of some form of energy being used. Now, there's four main forms of energy that we talk about in science and engineering. I want to take a look at the relationship between work, force, and energy in this short video clip.
To a scientist, work is only accomplished when a force moves an object some distance. A force is defined as a push or a pull. So even though someone may appear to be working hard to lift a weight, if the weight never moves, no work has been done.
Now, pay attention to the difference between our everyday definition of work. Usually in everyday speech, we say, work is how much effort we put into something. So even though the man may be putting effort into this, things don't move, there's no measurable result.
In contrast, if someone picks up a pencil and moves it to a new location, work has been done. Scientists use the formula work equals force times distance to calculate the amount of work accomplished. Naturally, to do any work requires energy. Energy is defined as the ability to do work. In the metric system, the Newton meter, or joule.
So a joule is defined as the amount of energy or the amount of work done to move 1 Newton 1 meter.
Is used as the unit of measurement for work or energy. So if someone moves something with a mass of 20 newtons 1 meter, he or she is doing 20 Newton meters of work. Remember, work equals force times distance, or 20 Newton meters.
Okay, there's four main forms of energy that we talk about in science and engineering. The first one is kinetic energy, which is energy in the form of motion. Okay, I want you to also forget what you think you remember from elementary school right here. In elementary school, they break things down, and it's either kinetic or it's potential. Now, kinetic energy is energy in the form of motion, but nothing ever really has all kinetic energy. It's not all related to motion. So kind of the way they think about things from elementary school was either one or the other. Nothing has just kinetic energy, okay? Maybe light might be the closest thing. Sometimes maybe people think of electricity, the kinetic energy of the electrons moving, but it also has potential energy with it. So things that are moving always have some potential energy. So even as something like this timer, if it's dropping, okay, it still has the potential to go further to the earth, even though it's moving. So it has both kinetic and potential energy. Anytime something is moving, it has kinetic energy. So part of its total is due to its kinetic energy. The amount of kinetic energy is determined by an object's mass and its velocity. And the equation is kinetic energy equals 1/2 the mass times the velocity squared. Now, when we said that nothing is pure kinetic energy, okay, when Einstein was trying to think about the total energy in an object, not just its potential energy, but all of the energy related to it, he basically was working with this equation, kinetic energy equals 1/2 the mass times the velocity squared. And then he said, well, it would be all energy if it was just kinetic energy. It was moving as fast as what he called the speed limit of the universe, which was the speed of light. So instead of v being velocity, he put in c, which is the speed of light, and then times the mass of the object. So it's the same equation, but it's just the maximum speed. So it would be all the energy in an object. And then because it's all the energy in an object, you don't need the 1/2. So this is where he came up with the equation E equals mc squared. Okay. Speed of light, that's the fastest speed or the maximum v. More mass means more energy or the ability to cause change. More speed or velocity also means that there's more energy or the ability to cause change. Okay, and then in elementary school, you learned about potential energy. And potential energy is energy stored in a motionless object. Once it begins moving, again, it still may have potential energy in it, but it also has kinetic energy. And we're going to talk about what it's called when things have both a little later in the unit. Okay. Only when it's motional is it all potential. If it starts to move, it'll have potential and kinetic energy. Okay. It can go through that change, but it's not changing GPE yet. GPE is the work to lift. So gravitational potential energy is the work necessary to lift an object. Okay. So let's take a look at this example. Okay. This girl's holding this ball up in the air here, and it's all potential energy because the ball's not moving. The potential energy equals the weight of the ball, which is the force times the distance lifting, or the lifting work. Work is a transfer of energy. So the work she did to get the ball up here is the weight of the ball times the distance lifted. When she drops the ball, and this is what I want you to think about, it took potential energy to raise it to the point where it is now, even though it's falling, but it's also moving. So it still has this potential energy to drop the rest of the way to the floor, but it's also moving. Okay. When it gets down to the floor, there's no potential or kinetic energy because it stops. So in this example, we would say all the energy has been removed from the ball. So when it was on the floor, it had no potential or kinetic energy. Then she did the work to lift it up to this position, and she added that amount of energy to it. During the time it was falling, some of the potential energy was going back to kinetic energy, but it has both at every position as it falls, because it still has the potential to fall further to the ground, but it is also moving. During this time when it has both, we call this mechanical energy. And we're going to talk about this more as the unit goes on. Okay, so gravitational potential energy is the energy added when something is lifted above the earth. And then the other kind of potential energy that we talk about being stored in objects is elastic potential energy, and that's the energy stored in things that stretch or compress. But I want to take a look at this short clip on exploring potential and kinetic energy. As I said, mechanical is when the energy is combined. That's the potential and kinetic energy. It's the energy when potential and kinetic energy of a system is added together. And a system is a collection of objects or things that are acting as a whole. So like your body is a system. So when you're moving, you have mechanical energy. A car that's moving has mechanical energy. So all of the atoms of the body or a cup creates a system of atoms. All of the moving and not moving parts of the body create a system of a human being. All the moving and not moving parts of a fire truck make a system of the fire truck. So it's the whole thing is a unit moving together. Now, in the next unit, when we talk about thermal energy is the energy of the atoms and molecules. So what we're doing is just adding up the moving vibration, the energy that they have. And that's different than when we talk about all the pieces moving. So is this whole system, like the whole fire truck, is moving? Okay. In other words, it's the complete unit, the large scale motion and objects interactions, all the pieces moving together. So I'm going to take a look at this pendulum. Okay, so it shows over here, this would be its maximum potential energy. Over on the other side, it would have its maximum potential energy. And then as it drops to the middle, this is where it would be going the fastest, at the bottom. Okay, so when it stops at the top for an instant, okay, so it's going up, and in order for it to go down, it has to stop for an instant as it turns around and starts going back down. Okay, when it stops for that instant, it would be all potential. Okay, and then same thing, if it lets go, it's going to go down and it's going to get to its maximum speed, and then it's going to go up and it's going to be going slower and slower and slower. And then for one instant, it's going to stop where it has to turn around from going up to be going back down. When it stops at the top for that one instant, it would be all potential energy at this point. As soon as it starts to move down, it has mechanical energy, because as soon as it starts to move down, when it's at this first position right here, okay, it has kinetic energy because it's moving, but it also has the potential to drop the rest of the way to the bottom. So it has both at every position between the top and the bottom where it has the maximum potential, maximum kinetic energy. All of this we would say is mechanical. And the same thing on the other side as it begins to travel back up, or if it was coming down from the top, as it starts to move down, it has mechanical energy. Right there at the bottom, it would have its maximum kinetic energy. So it would be all potential at this one point where it stops at the very top. And then as it's moving down, okay, it still has the potential to drop farther, but it's also moving. So this whole time in between, we would say that's the mechanical energy. At the bottom, it would have no more potential to drop further. So we would say, in this example, this would be kinetic energy at the bottom. And then as it starts to move back up, it's gaining potential energy again because it has the ability to do things based on its stored position. This would be gravitational potential energy as it goes up. Okay, but it's also still moving, so it has kinetic energy too. So in this whole time where it has potential and kinetic, this is what we call the mechanical energy. Okay, and then the last form of energy is wave energy. And it's energy that's carried in a wave from one point to another. And you can think about water passing as it moves to a boat, or waves hit the shore. The transfer of energy erodes the shore. You can see evidence of that energy all the time. There's also electromagnetic energy, which is energy that's carried in long waves and radio waves. So we're going to talk about the two kinds of waves energy, but waves carry energy from one point to another. We're going to stop here, and I want you guys to answer these questions on your own, and we'll pick up from here when we come back next time.